Look closely at your own hand. The exact same element pumping through your veins, binding the oxygen in your blood right now, is identical to the metal churning thousands of miles below your feet in the Earth's core. Iron is overwhelmingly dominant. If you could somehow put the entire planet on a scale and break it apart, you'd find that a massive 33% of Earth's total weight is pure iron. But there is a mathematical problem with that. This diagram shows the composition of the universe immediately following the Big Bang. It is entirely gas, roughly 75% hydrogen, 25% helium, and exactly 0% solid matter. Even today, billions of years later, astronomers classify any element heavier than helium simply as a metal. And all of those metals combined, every ounce of carbon, oxygen, silicon, and iron in existence, make up a mere 2% of the known universe. Since the origin of the universe produced absolutely no solid material, every physical component of our planet and every cell in your body had to be manufactured somewhere else. The internal engine of a star is a delicate tug-of-war. Crushing inward gravity is perfectly balanced by outward nuclear fusion. Over millions of years, it fuses hydrogen into helium, then carbon, oxygen, and silicon, building concentric layers. This process continues smoothly until the assembly line reaches iron. Iron possesses incredibly stable nuclei. It does not want to fuse with other elements. To force iron to fuse actually absorbs energy instead of releasing it. The moment iron is created in the core, the outward explosive pressure of the star instantly shuts off. With no outward force left, the star loses the tug-of-war. The entire mass collapses inward on itself under its own gravity in seconds. The extreme atomic stability of iron is exactly what causes the violent death of the most massive stars in the universe. The falling outer layers slam into the dense iron core and ricochet outward in an unimaginably powerful supernova. This explosion forges even more heavy elements in the chaos, blasting them across the vacuum of space at thousands of kilometers per second. But gravity never stops working. Over hundreds of thousands of years, that scattered dust cloud of newly forged metals slowly pulls itself back together. Driven by angular momentum, the cloud shrinks and spins faster, like an ice skater pulling their arms in. As rotation increases, centrifugal force stretches the cloud along its equator, flattening it into a protoplanetary disk, just like spinning pizza dough. Most of the material falls into the dense center and ignites into a brand new star, our Sun. But billions of tons of heavy element dust remain trapped, orbiting continuously in that spinning outer disk. Look at a model of our solar system today. All planets orbit the Sun in the exact same flat plane and direction. You are looking at the preserved rotational physics of a dead star's dust cloud. For decades, scientists struggled to understand how a vast, swirling cloud of microscopic dust could eventually organize itself into massive, solid planets. The first phase relies on static electricity. As microscopic dust grains bump into each other in the disk, electrostatic forces cause them to cling together. It works just like dust gathering on a static television screen, slowly building tiny pebbles into larger rocks. The tipping point arrives when these primitive rocks reach the size of mountains. At that scale, they acquire a significant gravitational pull of their own, forcefully ripping surrounding gas and dust out of the disk. This initiates a process called runaway growth. The larger an object gets, the stronger its gravity becomes. Stronger gravity pulls in more material, which increases the gravity even further, rapidly accelerating the rock's evolution into a massive planetary body. Planets are not born fully formed. They're the accumulated result of trillions of violent, chaotic collisions happening over millions of years. As these planets were forming, the young sun generated immense heat. This created a temperature gradient across the solar system, boiling away the lighter gases like hydrogen from the inner orbits and leaving only heavy, heat-resistant metals behind. That sorting mechanism dictated the architecture of our solar system. The orbits closest to the sun formed small, incredibly dense rocky planets like Earth. In the frigid outer edges of the solar system, where lighter gases were pushed, they collected to form massive gas giants like Jupiter and Saturn. Here on early Earth, the entire surface was a molten sea. Over time, the heaviest elements, primarily all that leftover iron, sank straight down into the center of the planet as it slowly cooled. That sunken, spinning core of molten iron began generating a planetary magnetic field. It acted as an invisible shield, deflecting lethal solar winds away from the surface, allowing oceans to stabilize and complex biological life to eventually evolve. The iron pumping through your veins, the ground beneath your feet, and the magnetic shield keeping our atmosphere intact are not separate phenomena. They are the recycled, reassembled debris of a massive star that had to collapse and die so that we could exist.